Okay. Since I did not get the recording made to go with this, I did put up a couple of recordings that would have helped you get started on this. I thought it might be a good idea to go over this and fill in some missing information maybe. Most of this you should have been able to fill in because we've actually covered everything on here except one or two things. And the one or two things that we've not covered, if you didn't know what it was and I haven't covered it, that shows you how important I thought it was. Okay? At the end of class, we will do a review for the quiz using Nearpod. But it will be a review for the quiz. It's going to be my way of taking roll today. It also will be a way to let me check and see if there's any gaps before you actually take the quiz on Wednesday. Okay? So let's get started. There are some problems, since I did not write this handout, there's some problems with the way that their notation is as opposed to the way that I do it. Now, if you've already got yours on Shovie, you can open it up and follow along and fill in any gaps you've got. If you have been doing this on paper and plan to upload it later, then you can go ahead and fill in your gaps before you upload it. But please take into account, these notes are not for a grade. These notes are for you, not for me. So if you don't upload those into Shovie, there is no grade associated with that folder. Okay? So, quick review of terminology here. The sample space is the set of all possible outcomes for a statistical experiment. An event is the subset of the sample space. This first one says, find the sample space for the experiment. Roll a six-sided die one time. What can happen if you roll a six-sided die? 1, 2, 3, 4, 5, 6. So the correct terminology uses a little curly bracket and it lists 1, 2, 3, 4, 5, 6, and then you close the bracket. Find the sample space for this experiment. You flip a coin one time. What can happen? Get it? Heads or tails? What if you flip the coin twice? That's exactly right. You could get two heads. You could get a head and then a tail. You could get a tail and then a head, or you could get tails on both tosses. Sample space for giving birth to one child. What could happen? Either a male or a female. Okay? Or if I didn't specify, B for boy, G for girl. Either one of those would be acceptable. Sample space for drawing one card from a standard deck of 52 cards. Do we even want to list this? No, because how many outcomes are there? There's 52 outcomes, one for each card. And all those cards are different, so they would be 52 different outcomes. Now, if I were going to list those out, for example, probably the way that I would start would be the King of Hearts, the King of Clubs, the King of Spades, and the King of Diamonds. And then all the way down to the Queen, and then the Jack, and then the 10, the 9, 8, 7, 6, and ending up with the aces of each one of these suits. Okay? At the top of this page, it tells you what the fundamental counting principle is. Just as a review, the fundamental counting principle says that if you have m choices on the first thing you choose and n choices on the second thing that you choose, then that means if you need to know how many different choices you can make total, you multiply the number of choices on the first one times the number of choices on the second one. It's better to look at this in context because it makes more sense. Suppose you're choosing a car from 3 different makes, Chevy, Ford, and VW, and there's 4 different colors to choose from. Now, the best way to do this is to make a tree diagram. So if you've got 3 choices for your first choice, Chevy, Ford, and VW. And then you've got a choice of colors for each one of those. And your choices of colors are blue, red, green, and yellow. Then you can see easily using a tree diagram that here you've got 3 choices. Here you have 4 choices. And the fundamental counting principle says that there's 12 different possible choices for your car. And those choices are the blue Chevy, a red Chevy, a green Chevy, a yellow Chevy, a blue Ford, a red Ford, a green Ford, and a yellow Ford, or a blue VW, a red VW, green VW, and a yellow VW. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 choices. So that's the purpose of a tree diagram, to actually list out the choices. If all you need to know is how many choices, you need the fundamental counting principle. So we drew the tree diagram, and we know that there's 12 ways to choose the vehicle. And what the fundamental counting principle says, you've got 3 makes times 4 colors is what gives you that 12. Now, if you're choosing an outfit from 3 shirts and 2 pairs of pants, how many different outfits are possible? You don't really need the tree diagram, because I didn't say list the number of outfits. I just said how many different outfits could you make? And you could make 3 times 2 is 6 outfits. You only need the tree diagram if you actually need to list out what the different outfits or the different cars look like. So using that same rule, an internet password consists of 5 letters. How many passwords can you make if each letter cannot be repeated? How many letters in the alphabet? 26. So you have 26 choices for your first letter, but you can't repeat that first letter. So how many choices do you have now? You only have 25. And then you only have 24 choices for the next one. Then 23 for your 4th letter, and then only 22. 1, 2, 3, 4, 5 different letters. And when you multiply that out, the answer's kind of surprising. Oops, one too many. I forgot my 26. 26 times 25 times 24 times 23 times 22 times nothing else is 7,893,600. And it says, well, how many can you make if every letter can be repeated? Well, that's 26 times 26 times 26 times 26 times 26. And your calculator, in order for you not to have to actually list all of those out, your calculator will take it also as 26 to the 5th power, because you're multiplying 26 times itself 5 times. So there's your calculator notation, and it's the same as this, 26 to the 5th power. And notice how many more you got. You now have 118 million, sorry. No, wait. 11,881,376 possible passwords. That's just by allowing things to repeat. So a Tennessee license plate consists of 3 letters followed by 3 digits, 3 numbers. Okay? How many plates can you make if each letter and each digit can only be used once? Well, there's 3 letters, so that will be 26 times 26 times 26. And then 3 digits, there are 10 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that would be times 10 times 10 times 10, except it can only be used once. That means that would become 25, that would become 24, that would become 9, and that would become 8. So if they could be repeated, it's 26 to the third power times 10 to the third power, because those would all be possible. But when you can't repeat, then you have to take that into account on your subsequent choices. So for the first one, we have 26 times 25 times 24 times 10 times 9 times 8. So we would have 11,232,000. But if you're allowed to repeat those, then it becomes 17,576,000. Would you like to have to list all those out? I don't think so. That's why it's good to know how to make a tree diagram if you're trying to actually list something out, but thank goodness we don't have to list these out. And then how many plates can be formed if letters can't be repeated, but the digits can? Okay, the letters cannot be repeated, so that would be 26 times 25 times 24, but the digits can be, so that would be 10 times 10 times 10. So then you'd have 15 million, wait, hard to count zeros on that calculator. Yeah, 15,600,000. Now there's actually 3 different kinds of probability. One of them is called subjective probability, and it's kind of like convenient sampling. It's pretty useless. That's when you just guess at what the probability of something is. Empirical probability is what we call statistical probability, which means that the results are based on observations from conducting an actual experiment. So for example, your experiment might be to flip a coin one time, and the event E would be getting a tail. So the sample space for that event, if you flip it one time, we've already looked at that. That's heads or tails, and that's it. So what that means is you have 2 outcomes. But only one of those is a tail. So 1 over 2 tells you that the probability is 1/2 or 0.5 or 50%. So the probability of event E, or the probability of getting a tail, would be 50% or 0.5 or 1/2. Now that changes if you flip it 10 more times. If you flip the coin 10 times, the probability that you get the first head is going to be 0.5. The probability that you get the next head is also going to be, or tail in this case, 0.5. And that's going to stay the same every single time because your coin doesn't remember what it was last time. So every time you flip it again, it's a 50% chance you're going to get tails. So what that's going to be is going to be 0.5 to the 10th power, and that's based again on that fundamental counting principle. So the total number of heads possible would have been 10. The total number of tails possible would have been 10. But the probability of getting 10 heads would have been 0.5 to the 10th power, just like the probability of getting tails would have been 0.5 to the 10th power. And notice what kind of answer we get. That answer is in scientific notation. And basically, when you see 9.76, even if my lab says round to 3 decimal places, you put 9.765 or 9.766 if you round properly, that's not right. You know probability can't be 9 point something, because the highest probability is if something's absolutely guaranteed. So what is the probability of something that absolutely has to happen? 100% or 1. Well, you know then you can't have something that's 976% of the time is going to happen. That doesn't make any sense. So that number out there at the end, that e negative 4, means times 10 to the negative 4 power. And what that means is that you need to move this decimal from where it is to the left, because it's negative 1, 2, 3, 4 times, which means you're going to need 1, 2, 3 zeros in front of that 9. So the correct answer for both of these would be 0.000097656, whatever. And if it tells you to round that off to 3 decimal places, what is that probability really going to be? Well, it's going to be really close to 0. It's going to be 1/1000th of a percentage, or 1/1000th. Now, if you change that to a percent, then it's 1/10 of 1%. Be sure that you can convert from decimals to fractions and percentages correctly, okay? But now think about this. How likely is it if you flip a coin, a fair coin, 10 times, how likely, instant, subjective-wise, how likely is it you actually get 10 tails? Or 10 heads? Not very good at all. You kind of know that. And this just backs up what you know. What do you actually expect to get if you were to toss a coin 10 times? What do you think you would most likely see? 5 heads and 5 tails. Would you be surprised if you got 4 heads and 6 tails? Or vice versa? No, that's not unheard of. What about 2 tails and 3 heads, or 2 heads and 3 tails? Oh wait, I didn't add them up to 10, sorry. 6 and 4 is possible, right? What about 7 and 3? Yeah, it's starting to be a little iffy. Okay?
Yeah.
So, 8 and 2, you'd be like, let me see that coin. Okay? And even 9, and especially 9 and 1. You're like, are you doing a trick or something that you're making this happen? If it's fair, you would expect 5 and 5 or 6 and 4. That would be possible. Even 7 and 3 could happen. But the others get increasingly less likely. Now we need to talk about something called the complement of an event. The complement of an event means that it doesn't happen. Either it's raining outside or it's not raining outside. Okay? Either you came to class or you didn't come to class. That's the idea of a complement. So if your experiment is to roll a 6-sided die one time and your event is rolling a 5, your sample space is 1, 2, 3, 4, 5, 6. But the probability of rolling a 5 is 1 5 out of those 6. Because there's only 1 5. The probability of not rolling a 5, and I don't use the overline notation, I like the word not, I know what that means. Probability of not rolling a 5 is 1, 2, 3, 4, 5 out of 6. Which is the same thing as 1 minus the probability that you did roll a 5. So that's what your complement rule means. It means that the probability of an event and its complement have to add up to 1. So if you know the probability something did happen, it's easy to find the probability that it didn't happen. So here's another example. Roll a 6-sided die one time. Sample space still the same. But what's the probability of rolling a number less than 3? Okay, there's your sample space. Rolling a number less than 3. That will be the probability of a 1 or a 2. That would be 2/6 or 1/3, because the only numbers less than 3 are the 1 and the 2. Now, if it said equal to or less than 3, you count the 3. But this said less than 3. So, what's the probability of not rolling less than 3? Which would be the same as the probability of equal to or greater than 3, because 3 is not less than 3, but it is itself, it's on the complement. So it's probability equal to or greater than 3, and that would be these other 4 numbers. And either one of those 2 expressions would be fine. Okay? Now we're still rolling that die. What's the probability, if you have this sample space, what's the probability that you roll a number greater than 6? 0. Because there's no numbers greater than 6. You can't get higher than 6. Which means the probability that it's equal to or less than 6 is what? That's the complement. It's not greater than 6. It'd be 100%. Because that's all the numbers that are equal to or less than 6. 1, 2, 3, 4, 5, 6. Is that far enough? Does anybody have any questions so far? Okay. At the top of this page, we have a definition of independent and dependent events. Independent events happen if the occurrence of one doesn't affect the probability of the occurrence of the other. If they're not independent, if one of them actually influences the chances that the other one happens, then we say that they are dependent. Okay? So dependent means one does influence the other. Independent means they have nothing to do with each other. They're not related or no influence in any way. So I want you to think about this and don't look for complicated definitions. Event A is that you complete all your homework assignments. Event B is your score on the test. Are event A and B independent or dependent? Dependent. Why do you think they're dependent? Okay. Now, so one does influence the other. Doing your homework means you probably would get a higher grade on the test. And vice versa, not doing your homework means you're probably not going to score as well on the test. So yes, there is an influence there. So these are dependent events. Event C is staying on a sensible, healthy diet, and event D is your weight. Does one influence the other?
Yes.
Yeah. Now, does it matter if I say weight influences being on the diet? No. I mean, likely, you know, if my weight's good, it doesn't mean necessarily that I ate a good, healthy diet. It might mean that I just exercise a lot. It might mean that I was just born with a really good metabolism. But does it have to work that way? No. Staying on the diet, does it influence your weight? Well, probably. Okay? There is an influence one way or the other. It doesn't have to be both ways. Okay? So here again, this is dependent events. Event D is the number of textbooks you purchased, and event E is the cost of your rent. Those are independent because does your rent have anything to do with how much you spend on textbooks? And does how much you spend on textbooks change how much rent you have to pay every month? Does your landlord say, well, you had to spend so much on books this semester, then I'm going to charge you half the rent this month? It'd be nice, but it's not likely. Okay, so those are independent events. Now we're going to talk about conditional probability. I did not write this handout because if I had, there's something here that I would have written differently. This B/A should be a straight line. And whoever made this handout obviously doesn't know that there is one of those straight lines on your keyboard. So I don't like the notation they use because it's confusing. It makes it look like what's the probability of a red marble divided by a red marble. That doesn't make any sense. So that line should be straight up and down. And that line means given that. Okay? So this says the probability of B occurring given that event A has already occurred. Okay? That's what that actually means. So if you have a bag with 5 red marbles and 5 blue marbles, and you're going to draw 2 marbles, notice here it says with replacement. That means you're going to put whatever marble you draw back in before you draw the second one. Okay? This says, what's the probability you draw a red marble given that your first marble was blue? Now, in order to actually have this happen, what has to happen on the first draw? You have to get a blue one. What's the probability of getting a blue marble out of that bag? 1/2. So that's the probability of getting the blue one to begin with. And you have to have the blue one to begin with before you can get the red one on the second draw. Otherwise, you're not going to get a red one after having gotten a blue one. So now that you've drawn your blue marble and you put it back in the bag, what's the probability of getting a red one? Still 1/2 because there's 5 red ones out of the 10. Because the way you should think of this is the probability of red on the number 2 draw given that you got blue on the number 1 draw. But you have to have both. It has to be a blue on the first draw and a red on the second draw for that to happen. And is what tells you you multiply. You're going to have to think through these in words. Probability of this happening and then this happens. Okay? So that's going to be 1 out of 4. What's the probability you get a red marble given that the first one was a red one? Is it any different? Yeah, they're being replaced. So that's still going to be 1/2 times 1/2, which is 1/4 or 25% or 0.25. Are these events independent? Yes, those events are independent. Getting the blue one is independent of getting the red one. Getting the red one is independent of getting the blue one because you put it back. Only because you put it back. So go to the next page. Look at the key difference here. Without replacement. Probability red number 1, or I'm sorry, red number 2, given that blue was number 1. What's the probability you draw the blue one? 5 out of 10 or 1/2. Okay, now let's assume you got the blue one. How many marbles are left in the bag? There's only 9. How many of the marbles that are left in the bag are red? 5. So that'd be 25 over 90, and at this point, I'm going to remind you that you can get a simplified fraction by hitting your math key after you type in the division and ask it to change it to a fraction, so the answer is 5/18. Okay? This is the same question as before, but again, this is without replacement. So this is the probability of getting the red one on the second draw, given that you got a red one on the first draw. So what's the probability you got the red to begin with? 5 out of 10. How many marbles left in the bag? 9. How many red marbles left in the bag?
4.
Only 4. So that's going to be 2/9, 20 over 90 or 2/9. Okay? Are these independent events?
No,
They're dependent. Why?
because it's like without replacement.
Yeah, and when you don't replace it, does this influence the likelihood that this is going to happen if you don't put the first one back in? Yes, it changed the probability on the second one. It made it, in the case of the blue one, it actually made it a little higher, but if it was the red one, it actually made it a little lower. So yes, the second one was influenced by the first one. So just remember, these are dependent. These were independent. And what made them independent was the replacement. Okay? From a deck of 52 cards, you're going to draw 2 cards with replacement. So that makes them what kind of events? Independent. Because if you put it back, it doesn't change the second one. What's the probability you draw a king on the second card, given that you had a king on the first card? Okay, there's 4 kings out of 52 cards. So there's your probability of drawing the first king. What's the probability now? And remember, you put it back. Shuffled it up again and draw again. What's the probability you draw the second king? 4 out of 52, because they're independent. I don't know if this is going to work or not. Oh, it did. So that's 1 over 69. Or 169, I'm sorry, 1 over 169. And even without converting that to a decimal, I know that's not very likely. That's pretty unlikely. So it was 0.0059. So if I round that to 3 decimals, then that's going to be 0.006, which is 0.6%. So again, those 2 events are independent because of replacement. So then going on to the last one on the page. Same experiment, change of words. Without replacement, what does that do? It makes them dependent. Which means when I calculate the probability of the second king, I have to take into account that one of the kings is already gone. It's laying on the table. Now, if it helps you to write these out in words like I just did there, that's fine. I'm not picky about notation on the test or quizzes. If you need to write it out in words, write it out in words. Okay, probability getting that first king, There's 4 of them out of 52. But then getting the second king, given that I got the first one laying out on the table, means there's only 3 kings left, and there's only 51 cards left. So that's 1 over 221. So notice that this is a lot less likely without replacement than it is with replacement. Let me see if I can. So if we change that to a decimal, it's 0.0045. Which would be 0.005 or 0.5%. So when there's dependent events, most of the time it means that your probabilities will be a lot smaller. Okay? Okay, same deck of cards. Probability that you draw a red card after you've already drawn the 3 of hearts. What's the probability of the 3 of hearts? So that's 4 out of 52. Now, it says, oh wait, no, not 4 out of 52. Whoa, 1 out of 52. There are 4 3s, but only 1 3 of hearts. Okay, only 1. With replacement, how many cards still going to be in the deck when I draw the second time? Still 52 cards. What's the probability I draw a red card out of those 52 cards? 13? Half the deck is red, okay? 13 hearts, 13 diamonds. So that's 26. So 1 times 26 is 26. Over 2,704. So that's going to be 0.0096, which rounded to 3 decimals is 0.010, or 1%. And those events are, since it's with replacement, independent. Now, same situation, except this time we're not going to replace. So the probability of the 3 of hearts is still what? Okay, because there's only 1 3 of hearts. Now we need the probability of the red card, only we didn't put the 3 of hearts back in. What happens to the deck now? There's only 51 cards in it, for one thing. How many of those cards are red?
5.
Only 25 because we have the red one out on the table. So it did change the probability, but not very much. So it's a little bit less than the other one, about 1/10 of a percentage point.
I'm more confused on like how to get it started out.
How to get started out on given probabilities?
Yeah, just like the 1 and the 52. I'm confused on just how it's started. And how we got one.
Okay, you're always starting out with your given probability. That's always the first one.
Okay.
The one that comes after the line is your first probability. Okay? Your second probability is what's in front of the line. And then if it's not going to be replaced, then you have to take into account that it wasn't replaced. Okay? As far as it being 1/52, it said specifically the 3 of hearts. How many 3 of hearts are there in the deck?
Out of the colors.
Okay, in cards, let's have a little cards list, because a lot of people don't. You know, if you don't play cards, then you probably don't know. So in a standard deck of cards, if you're talking about 52 cards, that means there's no jokers in the deck. There's usually 2 jokers. But if you have 52 cards, half those cards are red, and the other half of those cards are black. Okay? Which means you have 26 black cards, 26 red cards. Now, of those 26 red cards, half of those are hearts, and half of those are diamonds. So that means there's 13 hearts, and there's 13 diamonds. And the same thing with your black cards. Your black cards are divided into spades and clubs. And there's 13 of each one of those. Oh, sorry. Too far. And then the way the cards work is you've got, for each of these situations, you've got an ace, a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. So that's 13 possibilities for all of those. And since there may be people in here that aren't familiar, you're not going to remember this, I will put on any test we have over probability, I'll put on there what the breakdown of the cards is for you. Okay?
Thank you.
So again, just a quick reminder, this is without replacement. That means that we had one fewer card, we had one fewer red card from this 26.
But
And since we kept out the red 3 of hearts, then we only had 51 cards left in the deck. Okay? And these were dependent events because we didn't put it back in. So the multiplication rule down here, if your events are dependent, you multiply the probability of the first one times the probability of the second one, given that the other one occurred. If you're trying to find independent events and you know they're independent, then you take the probability of A times the probability of B, because B had no influence on A, so you didn't need to take anything into account. So if I'm looking at this question here, it says 2 cards are selected without replacement. What kind of event is it? It's dependent. And the way that you can write that without using the given that notation, find the probability of selecting a king and then a queen. The queen actually comes second, given that the king came first. Okay? This is always your first, because it's the one you know happened. And this is always your second one. So that's the way you'll always write that. And the probability of getting the king to begin with would have been 4 out of 52. And since we're not putting it back, then we're only going to have 51 cards, but we still have 4 queens. So that'd be 16 over 2652. And I'm not going to keep changing them to decimals and fractions. Y'all can do that.
If it was without replacement on finding a king, would it be 4 over 52 times 3 over 2?
If I didn't have without replacement, if I had with replacement, it would have been 4 out of 52 times 4 out of 52. Because that means you put the king back, you still have 52 cards. Okay? Anybody else have questions? Okay. Okay, same question. 2 cards selected, but this time it's with replacement. Okay? Probability of selecting a king and then a queen. So that's what that looks like. So the probability of the king, there's 4 out of 52. So there's that probability. And then, and always means multiply, a queen. Now, we replaced the king, so there's still 52 cards. And 4 of those 52 are queens. So that's 16 out of 2704. So again, that's 1 over 69, or 169, I'm sorry. The next one we've got says a coin is tossed and then a die is rolled. Find the probability of getting a head and then rolling a 6. So the 6, actually I wrote that backwards. The probability of the head and then rolling the 6. The head comes first. Getting the 6 comes second. But now let me ask you a question. Is this an independent or a dependent event? How do you know it's independent? Is that louder?
Different objects.
Two different objects. So is the coin going to look over and say, hey, I'm going to be ahead? No. They have no influence on each other. So this case, they're independent, and there's actually no difference in writing it that way and writing it this way. You're still going to multiply. It's just that there's no influence. So the probability of getting the 6 is 1/6. The probability of getting the head is 1/2. So your probability is 1/12. Yes.
On a quiz and exam, are you going to count towards credit for the answer to the question, how we write the probability equation?
No. No, I will expect you to know whether or not they were dependent or independent, but I can tell that because I will tell you that you'll need to write me the intermediate step. Don't just write down the answer. I've got to see all the steps. Okay? Probability a salmon successfully swims through a dam is about 0.083. Find the probability that 2 salmon successfully swim through the dam. Independent or dependent? Why?
Because it's 2 different fish, and just because the first fish gets through doesn't necessarily mean the second fish does.
That's right. That's exactly right. Now, or that the first one doesn't get through has any influence on whether or not the second one does or doesn't get through. So these are independent events. They're both going through the same dam, but they're going through by themselves. So the probability of the first one times the probability of the second one would be 0.083 times 0.083, or 0.083 squared. And that would be 0.006889. Which would be about 0.69%. I actually rounded that to 4 decimal places because sometimes they'll have you round probabilities to 4 decimal places. So be sure you're rounding correctly. If it was 3, it'd be 0.007, and it would be 0.7%. You've got 5 red and 5 blue marbles in a box. Without looking, you're going to take 3 marbles out of the box without replacement. Independent or dependent? They're dependent. What's the probability all 3 of them are red? Now that 3 red means you have to get the first one to be red. And the probability the first one's red would be 5 out of 10. Now the probability the second one's red is influenced by whether or not the first one was red. So if the first one was red, how many red marbles do I have left? How many left in the box? Okay. Now I gotta get the third one. What's the probability the third one's red? 3 out of the 8 that are in the box. And if you're going to put these in your calculator, I'm going to go ahead and show you now that it makes a difference if you use your parentheses or not. So if you put it in that way, it's 1 out of 12. If you don't put it in that way and you just string them in here, this is what you're going to do, and then you're going to get a wrong answer and not know why, so pay attention. 5 over 10 times 4 over 9 times 3 over 8 you still get the right answer. But that won't always happen, so be very careful. It's better to put it in the way I did at the top. That way you'll be absolutely sure. Using parentheses is a good idea. You always want to put parentheses around your fractions. So your probability is 1 over 12 and whatever that decimal is. Okay, same problem. With replacement, what changed? They became independent. Which means then that the probability of 3 red is going to be 5 over 10 times itself 3 times. 5 over 10 times 5 over 10 times 5 over 10. So it's 0.125 or 1/8. So we're doing okay so far? Okay, we're going to talk about 2 different words now. Please do not get these confused with independent and dependent, because they do not mean the same thing. Mutually exclusive events, which are also referred to as disjoint events, are things that cannot happen at the same time. Okay? If 2 events are mutually exclusive, they are guaranteed to be dependent. Because if A happens, not A can't happen. And if not A happens, A can't happen. If it's events A and B and they're disjoint and mutually exclusive, if A is what happens, then B can't happen. If B is what happens, then A can't happen. So that's mutually exclusive are always dependent. But the difference is that one precludes the other one happening.
What if the opposite's not true? What if one precludes, if A precludes B, but B doesn't preclude A?
It doesn't matter, there was still an influence. But then again, if A precludes B, but B doesn't preclude A, that doesn't mean that they're disjoint. They may not be disjoint or mutually exclusive. The exclusivity only goes one way. Okay, the influence is the dependence. Whether or not they can happen at the same time is the disjoint or mutually exclusive. It's mutually exclusive if one or the other can occur, but not both. Think about it that way. Now, are these two events, being a female and being a welding student, are they mutually exclusive?
No.
No, they're not. In fact, I'll go over there and get the two girls I know in the welding program right now and bring them in and show them to you. And they're better than most of the guys in the department. So these are not mutually exclusive or not disjoint. Event C and D, C is being male and D is giving birth.
Mutually exclusive.
They are mutually exclusive. Because so far, science has not given a way for that to happen. Event D is being an English major and event E is being a math major.
That's your dual major.
Can you be a double major? Yeah. So no, they're not. Okay? You could be a double major. Okay? Now, we've done these rules. I don't want you to get hung up on these rules because I'm not going to give you a bunch of problems like this. I'm going to probably give you a contingency table, which is far more useful to be able to read. But just going through this, you select a card from a standard deck. What's the probability the card is a 4 or an ace? First thing we're going to ask ourselves is being a 4 mutually exclusive of being an ace? Are those two things mutually exclusive? Yeah, you have to be one or the other. You can't be both. So the probability that it's this or that, that would be the probability of being a 4 added to, because or always means add, the probability of being an ace. And there are 4 out of 52 that are 4s, and there's 4 out of 52 that are aces, which is 8 out of 52. Which is about 15.4%. You roll one die, the probability of rolling a number less than 3 or an odd number. Now don't forget your sample space. This is my favorite thing to do. I always draw pictures. What's the probability of drawing a number less than 3? Okay, that'd be those two. Or an odd number. That would add those to the mix. Now, if you want to do it by the rules, the probability of a number less than 3 which would be the 1 or the 2, would be 2 out of 6. And the probability of a number that's odd would be 1, 3, 5. So that's 3. And if you look at that, you're going to say, but that answer is 5 over 6. You said it was 4 over 6. What did I count twice? One or 2, or an odd number. Counted the 1 twice. So you have to take the 1 out. And that's why it's 2 plus 3 is 5 minus 1 is 4 over 6. So this is what the rule tells you to do, but if you'll draw pictures, you don't need rules. You select one card from a standard deck, find the probability the card is a king or a red card. So we need to find the probability of the king. And the probability of red cards. Probability of king is 4 out of 52. Probability of red cards is 26 out of 52. Did I double count anything?
13.
I double counted the 2 red kings. So 4 and 26 is 30. 30 minus 2 is 28 over 52. Or 7 over 13. You roll 1 die, find the probability of rolling a number that is less than or equal to 3. So that, excuse me, that would be what? 0, that will be 1, 2, 3? Or a 6. Did I double count anything? No, not this time. Okay? So now we're going to do problems with the contingency table. And we've done these before. You should be able to do these by yourself. But I'm going to go ahead and do the first one with you. And then we're going to take time for a little quiz, a little pre-quiz in Nearpod. So it says use the information in the contingency table to answer the following. We have people that are classified according to whether they're Democrat, Republican, or Independent. We have a total of 140 people. 48 of them are CEOs, and 92 of them are blue-collar workers. We have 68 Democrats, 55 Republicans, and 17 Independents. What's the probability if we select one person at random out of that 140 people that we select a Democrat? Okay. Out of 140. Now, I'm not going to reduce the fractions or change to decimals. We're gonna focus on using the table. What's the probability we choose a Republican? Okay. What's the probability we choose a blue-collar worker?
92.
Okay. Now this next one, we need to be careful, because it says find the probability given that the person we choose is a CEO.
Big five of the
So we're looking at CEOs only. So yes, 48 people are CEOs. And of those 48 people, 5 of them are Democrats. Okay? The next one says the probability they're a Democrat or a CEO. And again, we've still got to be careful.
You have to add the Democrat and the CEO and subtract the
The CEO is a lead Democrat.
Right. We first have to look for the one that is a Democrat and a CEO. Because we have a total of 68 Democrats. A total of 48 CEOs. So we are going to take the 68, which is the Democrats, and we're going to take the 48, which is the CEOs, but we're going to have to remove the 5 that are both Democrat and CEO. And then we're going to divide by the entire total of 140. So this would be 116 minus 5 would be 111 out of 140. And we've already answered this question now because we know the one that are Democrat and CEO. That's where the overlap is. And then the last question is probability that they're blue collar, given that we're talking about Republicans. So that means we're only talking about Republicans. So conditional probability with a contingency table is a little easier because you know that you're just going to isolate the given condition. So that means we're only talking about these 55 people, and 21 out of those 55 people are blue collar workers. Okay? So the given condition gives you your denominator. Okay? Okay, I'm going to leave the last one for you to do. I will post the answers in Shovie to the whole thing so that you'll have the answers there to compare, and then if you've got questions you can ask them. But you need to get logged onto the computer or logged onto your iPad, one or the other. and go to Nearpod, nearpod.com, or use the Nearpod app if you've got an iPad or a tablet.